So, this is a secret message. Its contents are known only by me. I'll put it away safely and securely. Now, when you have some information that you wish communicated to only specific parties, be it a pen test report or your Netflix credentials, how would you ensure only your intended target was able to receive the message? I hope for everyone in this room, the answer was either some cryptographic solution or sod off, I'm not sharing my Netflix. As I'm sure many of you are aware, there is a looming technology that is set to change the landscape of cryptography. Quantum computers. They will force a change that's already begun. Although the NTSC, for example, predict that quantum computers won't be cryptographically relevant for another 10 years or so, the drive to move to cryptographic standards resistant to this new threat has already begun. In this talk, we will provide an introduction to this cutting-edge field, discuss paradigms for security testing, and the types of things to look for when offering remediation advice. Quantum cryptography and quantum-resistant cryptography are set to play increasing roles within our industry and day-to-day jobs in the next few years. So, before we begin, maybe I should introduce myself. My name is Imran. Hello. I have an MSc in theoretical physics. In specific, I studied gravity's particles in fields at the University of Nottingham. My MSc thesis was in quantum error correction to do with quantum computers, so this is a subject near and dear to my heart. During my studies, I participated in bug bounty programs and managed to find a P2 in a Fortune 10 company. This was largely the reason I was part of the group that was awarded the BugCrowd 2017 VIP Researcher Accolade. This ignited my passion for turning my hobby into a full-time career and became something I wanted to pursue. I was lucky enough to be able to join Cybrus in 2018, and I've been working there very happily as a security consultant ever since. And unlike every other company you've heard here today, we're hiring. So, with that out of the way, classical information theory. We'll talk about this a little bit just to give us a context for quantum information theory. So, classical information theory originates from Shannon's seminal 1948 paper, which put forward two important points. Entropy is a measure of information, and that it is possible to communicate reliably over noisy channels, provided the rate of communications is less than the channel capacity. So quantum information begins with the idea that there is no better system for the storage and processing of information than quantum systems. We're essentially already at the lowest level. Quantum mechanics deals with the building blocks of the universe. We can't go lower level, or closer to the metal, to use a coding term. We are at the lowest level language and are reaping all the performance benefits of such a language. Quantum information tries to extend Shannon's theory by replacing bits of information with generic 2D quantum systems called qubits, and classical channels by their noisy channel equivalents. In quantum cryptography, much like in classical cryptography, we would like to transmit and share information securely. Except this time, we're using the fact that quantum states cannot be learned without being disturbed. So, before we talk about quantum computers, let's have a quick recap of a classical computer. We know that information is stored in bits, ones and zeros, and that if storing one number would take 64 bits, storing n numbers would take 64 times n bits. Calculations are done essentially the same way as they are by hand. And as such, the class of problems that can be solved efficiently are the same as those that can be solved efficiently by hand. Efficiency referring to the idea that the evaluation time doesn't increase too rapidly with the size of the input. Now, with quantum computers, we use qubits instead of bits, as we've said, and they can also be in a state of 0 or 1. However, they can also be in a superposition of these states, say A0 plus B1, where A and B are complex numbers. We use complex numbers as they provide benefits in the comprehension and calculation of qubit states, such as the ability to map the positions on a sphere as shown in the image. Whereas a bit can either exist as 0 and 1, a qubit can exist in a continuum of states, confined by the boundary of the sphere, with poles at 0 and 1. Calculations are performed by mathematical operations called unitary transformations. These are done on the state of the qubit, and when combined with the principle of superposition, which we'll talk a little bit about later, this creates possibilities not available for hand calculations. This translates into more efficient algorithms for factoring, searching, and the simulation of quantum mechanical systems. Here we see another benefit quantum superpositions have, which is massive data storage, in fact, exponential data storage. We think back to our classical computer, where we had 64 bits to take up one number, or 64 times n bits to store n numbers. We can see here that it would be much quicker and much more efficient to store them on a quantum system. We could store 2 numbers with 1 qubit, 4 numbers with 2 qubits, and so on. There's actually an equation on that slide that, if you solved, would tell you how many qubits you'd need to store n numbers. I'll leave it to the mathematically inclined, and if anyone is really curious, you can come chase me down afterwards, and I'll tell you exactly how many qubits that is. So, quantum computers, are they better at everything? Well, quantum qubits rely on quantum mechanics to solve information, to solve certain problems much faster than is possible with a classical computer. In quantum mechanics, we depend on numbers called probability amplitudes, which can be positive, negative, or complex numbers. A simplification of this process is that we try and orchestrate it so that some of the wrong numbers have positive amplitudes, others have negative amplitudes, and when calculated, these effectively cancel each other out or destructively interfere so that the wrong answer isn't observed, and that the correct answers constructively interfere so that we see them. This is obviously a simplification, but is essentially how that process works. In general, problems that utilize parallelism are problems that are great candidates for being solved with quantum mechanical systems and quantum computers. Problems like prime number factorization or finding the most efficient route through a complicated city grid are great candidates, whereas you're unlikely to see much of an FPS increase in your favorite video games. Sorry to any Fortnite fans. So, I apologize if this slide is a little bit like teaching grandma to suck eggs, but we are going to have a quick look at classical cryptography, just so everyone's on the same page before we start talking about its quantum equivalent. So, with classical cryptography, we want, again, to allow secure communications of secret messages over public channels. We could use something like the one-time pad algorithm, where 2 parties, A and B, or Alice and Bob, use a one-time pre-shared key to encrypt information. An issue with this approach is that of secure key distribution, which has historically been impractical for most applications. So we can get around this. We can use something like a public-private key pair. This relies on the fact that certain mathematical tasks are computationally very hard. For instance, the factorization of a large number, at least on classical computers, into prime factors, as used in the RSA algorithm. In fact, the largest factored RSA number to date is 232 decimal digits long. This is with current classical or modern computers. And as computers become more powerful, larger prime numbers will be needed to be used in order to preserve the security of the algorithm. However, for quantum computers, Peter Shor showed in 1994 that they could solve such problems in polynomial time. Now, polynomial algorithms are considered fast algorithms. And on a classical computer, such algorithms could be addition, multiplication, square roots, and logarithms. These can all be done in polynomial time. And as such, you can imagine that when quantum computers come about, this will severely impact the security of RSA and any other algorithms that use similar techniques. So, quantum cryptography. It derives its many strengths from a few weird quirks of quantum mechanics. The first of which is no cloning theorem. Now, this states that it is impossible to create an identical copy of arbitrary, unknown quantum states. As such, intercept and replay attacks are inherently protected against, as we will see later. The second property is that of quantum superposition, which we've touched on earlier. It's when two or more quantum states can be summed to create another quantum state. Or it can also be thought of as that any quantum state is a sum of two or more distinct states. And as such, it is a principle that's critical to quantum computers. It contributes to many of the benefits that such systems offer. We will look a little bit more about quantum superposition later. Finally, we deal with entanglement. This is where the interaction of quantum systems results in a quantum state for each system being that they are no longer independent of one another. To talk about one system is to talk about the other, and to affect one system is to affect the other. This has massive implications for secure communications and the teleportation, although I hate that term, of information, with active research taking place in this field. So, quantum cryptography, it sounds great. It does have pros, but it also has some cons. First of all, a great pro is that it cannot be knowingly, or unknowingly in fact, intercepted. We will see this, again, as I keep promising, in more detail later. But due to the properties of the no-cloning theorem and quantum entanglement, it is impossible for information to be unknowingly intercepted. It's also secure, irrespective of computing power. The security comes from the underlying physical properties of these devices. It's baked into the universe, and it isn't something that can be cracked with greater computing power. Also, because of this security, the communications are secured at the physical level. Quantum cryptography can secure the complete end-to-end connection without the need for an SSL or VPN. However, as great as it sounds, there are some cons. It's expensive. Due to this being the cutting edge of cryptography, research and development costs are high, as are the fabrication costs of specialist components. This affects the final sale price. A factor that feeds into this is the fact that it requires independent infrastructure. For the requirement of exacting standards to be met, that's dictated by the need to entangle qubits, which we will see later. We need independent infrastructure capable of supporting quantum cryptography. This also has its own associated costs, and it's not cheap. Supercooling qubits and keeping everything magnetically sealed are just the beginning of the factors we have to deal with. There are practical problems in its implementation. As this is a very new technology, there are still practical problems to overcome. For example, fiber-based quantum key distribution, which I promise we will get to in just a second, can only travel so far. So I can make good on one of my promises, quantum key distribution. The goal here is that Alice and Bob want to talk without an eavesdropper, Eve, being able to learn their conversation, being able to garner the key they use to encrypt their information by eavesdropping when they set up their secure key protocol. The basic idea is that Alice and Bob use quantum systems to establish this key. And if Eve tries to learn the state, then she will inevitably disturb the system, and in doing so, reveal herself to Alice and Bob. Eve can sabotage the protocol, sure, in which case Alice and Bob won't be able to establish the key. However, the goal is to make sure that if Alice and Bob agree that the protocol was successful, then the chance that Eve knows the key would be very, very small. Out of a point of interest, BB84 is called such because it was proposed by Bennett and Brassard in 1984. Hence, BB84. Nothing to do with Star Wars. So, the steps of the BB84 protocol are as such. Alice prepares a qubit. She does so randomly in one of 4 states and sends it to Bob. Commercially, these are generally done with qubits being photons, or individual packets of light, and the 4 states being represented by 4 polarizations of that photon. Bob then measures this qubit that Alice sent over, and he does so in one of 2 bases. He does so randomly with a probability of 50-50 for each basis. Alice and Bob then reveal the basis in which the qubit was respectively prepared and measured. They do this via a classical channel, but they do not state the state of the qubit or its respective outcome. If the bases coincide, they add the bit to their list of key bits. Otherwise, they disregard the qubit. In order to make sure Eve hasn't tampered, they pick a proportion, say half, of the agreed bits and compare them using a classical channel. They should find no significant differences. If they find significant differences, say over the error rate of the communications channel, then they know someone has been messing with their system and Eve has been rumbled. So, is the protocol secure? Well, there are several mathematical proofs attesting to the security of the protocol. One such proof is provided in the further reading slide for anyone interested in the maths, but today we'll go over the intuition behind the proof. So the central principle is that in order for Eve to learn the key, the qubit sent by Alice must be intercepted and measured. If Eve knows the basis in which Alice prepared the qubit, happy days. She can measure it, she won't disturb the system, she can copy it and send it on to Bob. This doesn't violate no cloning theorem, it's perfectly happy because it was not an unknown quantum state. It was a state that she had already known. There is no physical device that can copy unknown quantum states, but this doesn't necessarily hold to be true with known quantum states. In this case, you can treat the information as if it was classical. The problem is Eve doesn't know the basis which was used by Alice to encode the qubit, and so she's left with two possibilities. Eve can choose one of the two bases randomly, measure in that basis, and pass the system on to Bob. If Eve chooses the same basis as Alice, just randomly, then happy days. Again, she measures in the correct basis, passes the state on to Bob, not disturbing it. On the other hand, if Eve chooses the wrong basis, then she will have altered the state of the qubit. And when she sends it on to Bob, it will be a fundamentally different particle to the one Alice had originally sent. When Bob makes his own measurement, there's a 1 in 4 chance that he will obtain Alice's prepared state. So a 75% chance it will differ. As we send more successive qubits, there is going to tend towards disagreement between Alice's final state and Bob's final state. Again, kind of revealing Eve's presence and tampering. So Eve's second option. The first one didn't sound particularly great. Let's see about the second. Eve can keep the system sent by Alice and measure it only after classical communications were sent between Alice and Bob. However, she needs to send Bob something. And since she can't copy the system that Alice sent, she doesn't know it, she has to essentially make up data. She will encode her own qubits and send them off to Bob at the same length as the ones she received from Alice. So she's essentially sending bunk data at that point. And the chances of her bunk data, her made-up data, being exactly the same as the data Alice sent are virtually nil. So using the first option, there's a small likelihood of success, sure, but that further diminishes as the number of qubits used in the protocol increases. And with the second option, there is no real chance due to the no-cloning theorem. So, in general, to wrap up about BB84, Eve can leverage more sophisticated attacks in which successive qubits are measured. This makes the proof a little more hairy, but ultimately, the heart of the proof is that information cannot be copied due to the no-cloning theorem, at least if it's not known. And that doesn't change, even with more hairy proofs. It's just the math looks a lot uglier. Quantum cryptography is fast approaching the stage of technical applications, with several companies in the process of producing cryptographic systems based on BB84. In fact, commercial quantum key distribution systems already exist. You can buy a pair of ID Quantica's QKD boxes for the low, low price of $82,000. Generally, in commercial systems, like I said previously, the 4 states of the qubit are implemented with 4 polarizations of a single photon state. Companies manufacturing such systems include Toshiba, ID Quantica, SecureNet, Quintessence Lab, and Magic Technologies. So, now that we know a little bit about the BB84 protocol, let's break it. What I want you to take away from this talk is a paradigm on how to approach pen testing quantum systems. Vulnerabilities can be broken down into 2 broad classes: inherent flaws and implementation flaws. Inherent flaws exist where an assumption was made during the creation of the protocol which doesn't hold to be true. A new mathematical technique or approach, for instance, may break the security of the protocol. An example of a protocol in classical terms with inherent flaws would be SSL version 3. Implementation flaws, on the other hand, exist because real-world physical systems aren't perfect, nor is our adaptation of theoretical principles to physical mediums. Such imperfections can be exploited to compromise an otherwise secure protocol. as we're about to see with what is called, quite sci-fi-like, the light injection attack. So, to begin the light injection attack, let's first remove a little bit of abstraction from the BB84 protocol and think about Alice and Bob's setup. So Alice is going to need some process for encoding qubits, generally some sort of photon detector, some sort of photon generator even. And for that, she can use a laser. That would be the most common way of doing it. Bob will need an observation machine to carry out the measurements. He can use a photon detector. So Eve can exploit hardware weaknesses in these components to compromise BB84. Eve can execute this attack against either Alice or Bob. Let's take the case of Alice to begin with. Eve sends a light pulse at one of the devices, in this case Alice's photon generator, and registers the reflected pulse. Because of the design of QKD's hardware, the reflected pulse will indicate which process or photon generator will be used by Alice to generate the next qubit. So now Eve does know the process in which Alice is about to encode her qubit. So now she can perform an intercept and replay attack with 100% certainty that she will be using the correct observer for each incoming qubit. Eve can capture the entire key this way, as Alice sends it, and then send qubits onto Bob without Alice or Bob being able to detect her presence. Using the information then communicated over the classical channel between Alice and Bob, Eve will be able to create the same key that they did. Now, if Eve targeted Bob as opposed to Alice, it would be a very similar process. Instead of learning Alice's encoding state, she'll learn Bob's detection basis. And when doing so, she will be able to measure Alice's qubits in the exact same basis as Bob. When Bob was correct, Eve will be correct, the qubit will be undisturbed, happy days, Bob adds it to his list, and they agrees with Alice. When he's wrong, when Eve is wrong, Bob is also wrong. So when he talks to Alice, Alice says, that's measured in the wrong basis, throw that qubit away. In either case, she gets to build the key alongside Bob, and her presence is never known. So this is problematic. How would we go about recommending a fix for the light injection attack? Well, fixes come in two flavors, or a combination of both. We have passive measures, which are inherent properties of the infrastructure that make them resistant to such attacks. Or we have active measures, the introduction of some tool or mechanism designed to mitigate the specific attack. So a passive measure would be for Alice to add an attenuator at the end of her output, at the output of her setup even. Eve requires then a more powerful laser to get a reflection that has any meaningful data in it for her to detect. Alice can double down on this by adding an optical isolator and a bandpass filter, which will inhibit Eve in her direction, but the optical isolator will allow photons through in one way. So Alice is getting her photons out, no problem. But Eve's struggling to get hers in and then back out with any sort of power enough for her detector to read useful information. In fact, the power requirements become untenable, like we're talking science fiction level. For this to work, we have to change from single photon states to weak coherent pulses, but that's just a small technical detail, and it shouldn't affect the protocol in any way. It's just you can't really use an attenuator with a single photon. An active measure would involve using some sort of detector to warn Alice and Bob should average and/or peak power of an incoming pulse rise above a certain level. This would this would warn them that someone is trying to enumerate either detection bases or encoding bases. Also, we can use a combination of both, as I've quite helpfully put there. So, in conclusion, there is no better physical medium for storing and processing information than quantum systems. This is according to quantum information theory. Quantum cryptography can be secured on the physical level. There are many pros, but also several cons, and physical hurdles yet to be overcome. Commercial systems relying on quantum principles are already beginning to emerge. IBM have just announced their first commercial quantum computer, the Q System 1, and aim, to some degree, to bring quantum computing to the masses through their cloud platform. In addition to this, commercially available QKD systems are already with us. The landscape of cryptography is changing under our very feet, as I said at the beginning, and it's up to us to adapt to it. With the introduction of new protocols, some completely secure in theory, there still exists many pen testing applications in the physical implementation of these systems. If you can't find an inherent flaw, look for an implementation flaw. What components were used? What are their technical limitations? How can these limitations be abused or protected against? Technical details for many components are publicly available, and so research into the compromise of these devices can be done without even having to have one in front of you. Here is the further reading I promised. There is a proof there for the BB84 quantum key distribution protocol. There are also other papers that I found particularly useful in writing this talk. Here are the obligatory image references. And I would like to thank Cyberus, who have been awesome and allowed me the time and resources I needed to put this talk together, Mark Crowther, Catherine Fair, and Ian Lonsborough for their guidance and encouragement, Crest for providing such a stellar platform, and you for listening. Thank you.